In this video, I'm going to show how we can get from what I have written here, which is the time-dependent Schrodinger equation. So that is the Schrodinger equation, which is dependent on time, and we want to see how we can get from this. So if we call this the time-dependent Schrodinger equation, we want to see how we can get from that to the time-independent Schrodinger equation. And so to do this, it all kind of hinges on this one technique in differential equations called the separation of variables. So separation of variables. And this is sort of like I said, a mathematical technique, which I'm not going to explain in full detail, except to say that this works in sort of specific cases, and the Schrodinger equation just happens to be one of those cases where this works, or at least the solution. It works for solutions of the Schrodinger equation that actually correspond to reality. And to do this, so I have this written here with our wave function shown explicitly as a function of space and time. So we want to separate that spatial and that time variable out. And so we will end up with something that looks like this. So this is our wave function that's a function of both space and time. And we can set that equal to a product of the wave function as just a function of space multiplied by the wave function as a function of time. And so now we've separated our variables into two things here, two different functions that are just a function of a single variable, but multiplied by each other. And so that is sort of the big hurdle that we have to jump over here. And then the rest of it just kind of falls out of that, sort of. And so now we can rewrite, here I'll put this so you can actually see it still. We're going to rewrite this, but with our wave function equal to these. And so that will give us I h bar multiplied by the partial of so our phi, which is x, multiplied by our t. And so that is still over just t, which we have up here. And that is equal to minus h bar squared over 2m multiplied by the second partial of our phi as a function of x multiplied by t as a function of time, over still just just with respect to space here, plus our potential multiplied by phi with respect to x, t with respect to time. And so now I've just rewritten this here using this relation right here. And so from this, what we can do is, so from here we can actually just divide through by, well, I guess multiply through. So we just take this whole thing and multiply it through by 1 over phi as a function of x, t as a function of time. And so what we get from that is, so the t here and the t here will cancel out. So we end up with, well, I think I skipped a step here. So usually what you do is you kind of pull out the things that are not changing with respect to this variable. So we would pull this out like this. So phi as a function of x, and then we would just have t as a function, and this actually changes it to a full differential here. So d t as a function of t over time, because now we're only looking at this as a single variable. We don't have that x. Uh, this is not a function of x, so this can just become a full differential here, and then that will be equal to minus h bar squared, and we will now have our t pulled out on this side, and this is over 2m, because now we are just looking at the function of x here. So this is the only thing that has to remain in the differential, and as I said before, that actually makes it into a full differential here. So phi is a function of x, and then x there, and then we would keep this. So I skipped this step here at first, but this is kind of an important. I mean, it doesn't make a big difference if we skip the step, but it's important to show sort of what's going on here, because now if we multiply through by this, then what we have is on this side, this phi as a function of x will cancel out with this, and on this side, this t as a function of time will cancel out with this, and with the potential, both of them will end up being canceled out. And this is an allowed thing in algebra because we're multiplying all sides by the same thing, so we're just doing the same thing to all sides. But then what we end up with is on this side, because this and this cancel out, but we still have this t as a function of time there, we still have I h bar, and I'll just put this down here, and then we have dt as a function of t over dt, and then we have that equal to minus h bar squared, and that's 2m, and now we still have this this phi here because we've canceled out this t as a function of t with this one, but we still have this phi as a function of x right here, and then we still have this this phi as a function of x changing with respect to x here, and these two things cancel out with those, so we just have v right there. And so this side over here is a function only of time, and this side over here is a function only of space, or x. So it's a function only of space there. So what that tells us is that this must be constant, because if we're changing with time over here, this would not be changing, so this also can't change, and sort of vice versa. This only changes with space, but since this doesn't change with space, then it would be constant, and so this all has to be constant. And so we could take all of this and say that our I h bar over the t with respect to time, dt as a function of t over dt is equal to some constant, which is also equal to minus h bar squared over 2m phi as a function of x, second part, or second full differential of phi with respect to x, dx squared plus v. And so we know that there is some constant here that these are both equal to, and we will suggestively call this constant e. So then if we just use this right here, we can say that minus h bar squared over 2m phi as a function of x, d d squared phi as a function of x with respect to x plus v is equal to e. And so from here, then what we can do is multiply everything through by phi with respect to x. And what that does is it'll cancel out right here and then multiply both of these sides by phi as a function of x. So we have minus h bar squared over 2m, and then we have our second differential here of phi as a function of x with respect to x plus v phi x equals e phi x. And so this tells us so we have this differential here, this second differential plus our potential here multiplied or acting on, I guess you could say, this wave function that's only a function of space equals e. E acting on this wave function that's only a function of space. And so we see here we no longer have any time involved here, and so we could even separate this out further. We could factor out the phi as a function of x and say that we have minus h bar squared over 2m d dx plus v, and then we put that in parentheses, and this is now an operator. We can say this is an operator acting on this wave function equals e multiplied by this wave function that's only a function of space. And you might recognize this as the Hamiltonian operator. So the Hamiltonian operator. And we see now that we are in that form that we've talked about before of a Hermitian operator acting on something, giving us an eigenvalue multiplied by that same function there. And so we are now in that form. So we could even write this in what you may have seen before. So this is still phi, but you will often see it written as psi still, and I'll just put that is a function of x equals e psi as a function of x. And so this is kind of that canonical time-independent Schrodinger equation where we have our Hamiltonian operator acting on our function, which we now know is an eigenfunction. So is an eigenfunction. And so then this E here, which is energy, is our eigenvalue. So that's our eigenvalue. And so we know that value. So we know that energy, the energy of the system must be an eigenvalue for this Hamiltonian operator, and that these wave functions must be eigenfunctions of this Hamiltonian operator. And so this tells us that there are going to be just particular energy levels, and so that's kind of how we get the quanta of energy from this. And if you sort of looking ahead at chemistry, so you may have heard of the quantum numbers. So you have things like the principal quantum number. You have the angular momentum quantum number, which I think is usually denoted as a lowercase l, and the magnetic quantum number, and then spin. But the principal quantum number is the energy. And so that is, these principal quanta are the eigenvalues of this equation for this Hamiltonian operator. And so that's where that comes from. And in chemistry, we don't use like the actual number. We just say that the principal quantum numbers are 1, 2, 3, 4, and so on. But those each have an energy associated with them, and that energy would be this energy right here. And so that's why in chemistry, so this is the, as I said, the time-independent Schrodinger equation. And so that's why you would, in chemistry, well, I guess in physics as well, it's not like chemistry follows different rules, but I'm a chemist, so I learned about this stuff through chemistry classes. The first principal quantum number is that that circle, that s orbital, and then with 2 you end up with something that looks like this, and then 3 you start getting more complicated structures that look something more like this, and so forth. And so the shapes of these orbitals is determined by the energy for them. And so we know that this is time independent because this s orbital, I mean, you know, you could say that the electron is sort of moving around inside this cloud, but the shape of this orbital, which is actually what our Schrodinger equation is giving us. That's the shape in space. That's why it's just a function of space. That doesn't change over time, and so that's why it's time independent. And so when we start getting in later videos more into solutions to the Schrodinger equation, I will show sort of how these shapes can fall out of the time independent Schrodinger equation. And so we will start talking about that probably here in a few videos, but there's some other things that that we need to get through first before we start getting to actually solving the Schrodinger equation. But anyway, I hope you found this enlightening, and I will see you in another video.